Okay, let us move forward with the closed network. So, closed network, as we all know, so far there it is a 3-stage network. So, it will consist of the switches in the first stage, and we define them as M1 by N1, and there will be R1 such switches, and in the middle stage we will have R1 by R1 switches. Each one of them will be N1 by N1. In fact, I had written in the beginning that it will be M2 by N2, M3 by N3. So, we can actually do that, M2 by N2 and their total R2 number of switches. We have N3 as the output and M3 as the input in the last stage, and I can connect these. So, in total there will be R3 switches here, and when it is a symmetric situation, R1 should be equal to R3, M1 should be equal to N3 and N1 should be equal to M3. So, of course, we had also written down, by looking at the picture or the drawing, we can actually establish that N1 should be equal to R2 should be equal to M3. Okay, there is exactly one line which is coming in. So, closed network has this characteristic of one line, and similarly on this side your R3 should be equal to N2, your R1 should be equal to M2. Okay. So, this typically is the closed structure. Now, the question is, when I actually explained the condition for strictly non-blocking nature of a switch, I said there is one free port here which can actually connect to any one of these middle stage switches for onward making the connections. There is one free port somewhere here which can be connected to the middle stage switches. Basically, if except this one, which is the free port, except this one. So, remaining ones which are going to be M1 minus 1 can be connected to middle stage switches, so that they are connected to some other places. On this there will be N3 minus 1 switch ports, outgoing ports, which are connected to the again middle stage switches. So, the set to which these busy ones M1 minus 1 ports are connected and set N3 minus 1 are connected, they are different sets. So, if I have one additional switch that can be used to set up a call from this free port to this free port, and then we came up with a condition that my R2 number of middle stage switches has to be greater than or equal to M1 minus 1 plus N3 minus 1 plus 1. So, the switches has to be greater than or equal to this number. We actually then arrived at a condition that R2 has to be greater than or equal to M1 plus N3 minus 1. Okay. Now, question is, can I represent this whole thing in a different fashion? So, I did it through an argument, which is fine, but there should be a better method of visualizing it. So, one of the best methods which actually can be done is known as Paul's matrix. It is a pretty powerful abstraction, or the way by which a closed network actually can be represented, all connections. Okay. Now, how this actually will be done? So, let me build up a closed. So, what will be the dimensions of the closed network? That is the first thing. So, I have actually rows in this. So, rows will represent what? and they are columns. So, columns has to also represent something, and in a corresponding cell what is going to be entered. So, these three things has to be identified. So, the way it happens is the pulse matrix typically will be having, for example, we will say we will actually call it as a switch. I can draw it here. So, there is a switch number A, it can use lot of middle stage switches. Okay, I can call them as, and there is a switch here, I call it B. Okay, and then these one are F, there is a possibility of G, there is a possibility of H. So, if F, G, H are connecting in this fashion, then I can have other ones I, J kind of thing. So, this is connected to some other one, say B2, this is connected to B3. See, it does not matter to which input port in the A switch this line is connected, because this is a strictly non-blocking switch. So, these ports does not matter. So, I have to worry about from this switch A which particular path has been used to connect to which particular switch in the output stage. So, these ports actually does not matter here, these ports are immaterial. So, what I will do is I will use these switch IDs to represent my rows. So, there will be a row A corresponding to the switch A. So, how many rows will be there in this pulse matrix? So, how many possible first switches which can be there? These are R1. So, you can have R1 rows. So, I will write down when the conditions for a pulse matrix to be legitimate or legal or the correct matrix to represent a closed network. So, one thing which is clear from here, there has to be R1 rows, and what we do is the columns will be representing the switches in the third stage or the output stage. So, how many switches are there in the output stage? These are R3. So, we will have R3 columns, and I am again not worried about the outgoing ports, I will be worried about the switch. So, a column will be represented by P, for example. Now, from A to B, I have created set up a call via F, via G and via H. So, I can actually put F, comma G, comma H here. Okay. So, the important thing within a cell AB, so row corresponding to row A and column B, I need not have there is no restriction that how many entries can be put. There can be more than one entries which can be put here. Okay. And that is what the pulse matrix is all about. And of course, similarly, if I have connected A to B2 via J, so I have to find out where the B2 is. B2 is somewhere here maybe, and I can make an entry J. I can find out where the B3 is there, and in that column I can make an entry this was I. So, I can make an entry I. So, now if you look at it, how many possible entries I can make in row A? Let us look at that. So, that will be governed by number of switches which are there in the middle stage. For every connection, now remember what I am considering here is a unicast connection. There is only one input, there is only one output which is there. Okay. So, when I am connecting one input and output gets consumed, one connection goes through. So, if this connection F has been consumed, F cannot repeat, F cannot be used to connect to B2 or B3 also simultaneously. I will come to a case when that will also be feasible. So, this actually implies the number of entries in a row will be restricted to number of middle stage switches. So, there will be R2 possible entries which can be there, that is one argument. But how many connections I can set up from the switch A? So, those will be basically decided by number of input ports. So, number of input ports which are coming in is M1. Of course, number of middle stage switches and number of incoming ports are two different things. So, I can increase these, I can reduce this. So, my number of elements here cannot exceed R2. So, they have to be less than R2. They also have to be less than or equal to M1. So, if M1 is smaller, it cannot be greater than M1 actually, it has to be lower than M1 number of elements in the row. So, which actually implies the number of elements has to be minimum of these two whichever is there, M1 and R2. So, they should, this number of elements in row will satisfy this condition. Similarly, for the columns also, if you want to estimate, I cannot have, because there is exactly one path coming here. So, at most all these number of middle stage switches, it has to be lesser than that. Okay. Now, there is a possibility when number of middle stage switches are less than the number of input ports or number of outgoing ports, then the minimum of these two will be R2. Okay. So, similar conditions exist. This is for number of elements in a row. So, similarly, there will be number of elements in a column. So, they have to be less than R1 or they have to be less than N3. So, they will be essentially, because they cannot be greater than these two values. So, I can write down they have to be less than minimum of N3 and R2, sorry, this has to be R2, is a very similar condition which also happens on the elements in the column. Okay. If for example, this B is also connected to J and then it is being connected here. So, this is some element say C. So, I can define a row C and the B is connected via J. Okay. So, this is how typically the pulse matrix will be filled in. Now, if you look at a pulse matrix, can you identify whether it is correct or not correct? So, one thing which is sure, if my number of elements here are more than this, then there is certainly a problem, it is not correct. Or if number of elements in a column are more than this, then there is a problem. Okay. So, let us look at, write down the legitimacy conditions for the pulse matrix. So, we will use this pulse matrix in now all of my theorems to figure out the conditions for strictly non-blocking nature and rearrangeably non-blocking nature. So, the first condition, as we have done it through discussion, so I can very well write it, that each row can have at most M1 symbols. So, because maximum number of paths from a switch to the middle stage switches can be equal to number of incoming ports, is because of that. Second is each column can have at most N3 symbols. So, the first one was corresponding to this, the second one is corresponding to this statement. Okay. Again, this is because those many number of output ports are only available. So, those many middle stage switches can only be occupied or can only be connected. Okay. The third statement which goes Now this is important. Symbols in each row must be distinct. Okay. So, there are R2 distinct symbols, that is why we can have at most maximum R2, and why these need to be distinct? Because if they are not distinct, then what is going to happen, let us see. So, I will have a switch now. A symbol actually has been repeated, that is what I am telling, that in this case if this is A, this is B, and symbol has been repeated. I repeat a symbol, say F here, G here, G here. What does it mean? I am connecting via F to some switch which can be V4 here. I am connecting F to B, and F also being used for some B5. So, which actually means I am connecting here, and then F is being connecting here, F is being connecting here, F is being connecting to some other ones. So, this is B4, this is B5. What does it mean? So, some input signal information is coming, is being routed by this crossbar to the middle stage 1, and middle stage is connecting to all 3 simultaneously. It is splitting the signal, is making 3 copies and transmitting it to these switches, which then of course can further split if they wish, or they can have only one outgoing port. Splitting here does not matter, because it is a strictly non-blocking switch. Okay. So, this scenario is a multicasting scenario. So, number of elements actually can be more than M1 and R2, but they will, and they may not be distinct actually, but this number of distinct symbols. So, if the repetitions are being only counted once, then this condition will always be, this limit has to be still satisfied. Okay. So, this multicasting is happening, and I was not considering multicasting in the beginning. So, similarly we will have fourth. So, all elements which are being used, they are all distinct. So, there is no repetition, that is what the condition 3 for a unicasting case 1 to 1. The fourth condition will be that the symbols in each column must be distinct. Now, we have to understand, if these are not distinct, what is going to happen, and that will give us a reason why they should be distinct. So, let us see. If the symbol in each column are not distinct, they are not different, I am repeating a symbol. Okay. So, I might repeat, so I have got F, G, H, I may repeat that from C also I am going to put an F. Okay. So, A has been used to connect, so this connection is not required, only it is connected to B. Okay. And this is F. So, F, there is a G through that also, H through this also is being connected, but interestingly I am also connecting to B via B, and C also via F. So, there is some C which is sitting here, and I am connecting it to F and connecting it to B. So, there is only one line here and there are 2 lines here. It means there are 2 circuits, 2 paths which are coming and they are merging here. It means 2 signals two separate input signals which are coming from the input side are being put on a same line, they will interfere. So, this is actually illegal, this is not permitted. It is immaterial whether it is a multicasting or a unicasting, even for a multicasting or unicasting both cases this is illegal. So, column elements have to be distinct always, okay. And there this actually means the number of symbols are going to be, and at most R2 symbols can be existing. And in this case at most R2 symbols. In case if we do allow multicasting, then I have to do away with this condition, third condition, that the symbols have to be distinct in the row, they can be then repeated. So, there need not be at most R2 symbols, okay. And of course, each row can have at most M1 symbols, this condition will also not be true. I can actually repeat, so F can repeat multiple times and henceforth I can have more than M1 symbols, that is possible. So, that binding condition goes away and they need not be distinct. So, condition 1 and 3 need not be satisfied for multicasting. So, whenever you have multicasting case, condition 1 and 3 need not be satisfied. Okay, so that is what the Paul's matrix is all about, and that is how we can represent a 3-stage closed networks in a Paul's matrix. Okay, now once we understand what the Paul's matrix is, we have to now look at the clause theorem. So, essentially the strictly non-blocking property for a unicast case or one-to-one connection, the same I am going to now formally put up as a theorem. So, this theorem is because of Charles' clause and this is known as clause theorem. Okay. So, theorem states that a closed network is strict sense non-blocking. Remember, in strict sense means that existing connections will not be disturbed. So, without disturbing the existing connections, we can set up a new connection if the input and the output ports both are free. Is a strict sense non-blocking here. If and so, if implies it is a necessary condition, only if implies it is also a sufficient condition, you do not have to satisfy anything else, this is good enough. The number of second stage switches R2 is greater than or equal to M1 plus N3 minus 1. So, when I had explained the same thing to you earlier, I have not given you the condition for sufficiency actually. I have never proved that, I only said this is a necessary condition. Okay. And of course, in particular for symmetric network, that is M1 is equal to N3 is equal to n if and only if R2 is greater than or equal to 2n minus 1. Okay. So, that is the clause theorem. So, let us start with the proof. So, we will say let an input from switch A wants to get connected to an output of switch B. The connection is made by putting a middle stage switch entry in cell AB of the pulse matrix. Okay. So, we have to ensure that we should be able to find out an element without violating the legitimacy conditions of a pulse matrix. So, the logic actually goes very simple. The argument I have already given, I am now formally writing it. Okay. There can be at most m1 minus 1 distinct entries already in row A, and I am talking about a distinct entry. So, there is no multicasting here. Okay. There can be only m1 minus 1 elements which can be there. Okay. Why m minus 1, m1 minus 1? Because there is one free port which is there in A which I want to connect to a free port in B. Okay. So, there is one free port, so their maximum number of incoming ports is m1. So, number of occupied ports can only be m1 minus 1. So, there can be at most only m1 minus 1 distinct entries already existing in the row A. I can actually take the same logic, and this is a worst case scenario, there can be less also. It is not that when an input port has to be connected, these many distinct entries has to be there. This is a worst case scenario when all other neighboring inputs also connect to the switch A are already connected to somebody. This is a worst case scenario I am taking. In a better cases there can be less number. So, I am looking at even in worst case scenario I should be able to set up a connection. So, the next one is using the same logic, column B can have n3 minus 1 distinct entries. So, same logic holds true here. So, because there is one output port which is free at switch B, only N3 minus 1 other output ports in worst case are already connected. So, corresponding to each one of those, it is a point to point connection, there will be N3 minus 1 distinct entries in the column itself. Okay. Now, this actually means if I draw the matrix, so there is a row A which has already got some entries which has M1 minus 1, there is a corresponding column which is for B, I have entries which are N3 minus 1, I need to find out an element which can be put here. In again worst case scenario, these M1 minus 1 and N3 minus 1, the number of entries which are in column, which are in row and which are in column, they do not have any overlap. So, the entries, this N3 minus 1 entries, let me call it the entries for B actually. So, this particular set and the corresponding entries here, these are AE entries, and in worst case scenario AE intersection BE is null. Okay. So, which actually means AE union BE, the cardinality of this particular set should be M1 minus 1 plus N3 minus 1. I need one extra, if I have one extra switch, I can put that switch here, middle stage switch, which actually means whatever is the cardinality of this union, my middle stage switches R2 should be greater than or equal to cardinality of AU, AEBE plus 1. If that is true, then I can actually put that element here. I do not have to disturb any existing connection and I can set up the path, okay, which implies that R2 should be equal to greater than or equal to M1 plus N3 minus 1, and that is a condition for the closed network. This actually means that this is necessary and sufficient condition for setting up of the path without disturbing any existing connection. Okay. So, that is what the clause theorem is all about.